Recording in progress.
Yeah, cams on everyone. Let's start off. So the last thing that we did. Yeah, so last thing that we did, we started with the calorimetric introduction. Great. Others cams on? Great, let's go ahead with this. So consider, so we are trying to find the relation between the heat given and the temperature. We know when I give, when you give heat, temperature rises, but exactly how? Consider a body of mass m at temperature T. Let dq, so dq is your small amount of heat. Right, be given and temperature rises by dt. So we have a body here at temperature T. You gave heat dq. In this process, the temperature of the body has increased by dt. So the formula here comes out to be, so dq is given by ms dt. So the total heat given will be integral ms dt. So if your m and s are constant, it will become delta t there. So m is the mass of the body. S here is nothing but 1 by m dq by dt. This is also called as specific heat capacity. We got a bit of a theory. So what is the specific heat capacity? So specific heat capacity, right? It depends on the nature of the material, right? And the substance basically. So what is the physical meaning of this? Higher the specific heat capacity, more difficult to change the temperature. Look at this equation here. Huh? dt is q by ms, meaning the bigger the value of s, the lesser the change in temperature. So if a body has a higher specific heat capacity, means it is very difficult to change the temperature. You have to provide more heat for the same temperature change. Higher the specific heat, more difficult to change the temperature. That's the physical meaning of it. There. You can put on the thing in the red box. Clear with this? Now see. So we use dq is equal to ms dt. S is equal to 1 by m dq by dt. This we use for solids and liquids. Now, for gases, right, mass really doesn't make sense. So for gases, we use dq is equal to nc dt. You must have studied this in chemistry. Here n is the number of moles and c is called the molar heat capacity. So for gases, moles is more preferable. It is the amount of heat required to change the temperature by 1 degree per mole. Yeah, so technically speaking, right, this m into s can be written as n into c. They are one and the same thing. So when you study gases, we prefer to study in terms of moles, and for liquids and solids, we prefer to study in terms of kgs. Clear with this? There. So the only new thing I taught you today is dq is equal to ms dt. We are going to play with that one thing in the entire class today. So there are a few values which you need to remember. Specific heat capacity of water is 1 calorie per gram per Celsius. Meaning if I give 1 calorie to 1 gram of water, it will change the temperature by 1 degree. Specific heat of ice and specific heat of steam is half calorie per gram per Celsius. So for a ice block, if I give half calorie, the temperature will change by 1 degree for ice and steam. Generally, they will give you the values, but better you remember them. Clear with this? So let me ask you a theoretical question. If you're constructing a thermometer, so for a liquid in a thermometer, remember the mercury thermometer? You have a bulb here. If you guys remember here, this one. So we have a bulb here filled with mercury, and when you give some heat, the mercury level rises. It should have two options: less specific heat, less quotient of volume expansion; high specific heat, high quotient of volume expansion; less specific heat, high quotient of volume expansion; more specific heat, and less gamma. So they'll play around like this. It should have what? Specific heat. Should it be high or should it be less? Gamma, quotient of volume expansion. Should it be more or should it be less? What do you guys think is the answer? If you're constructing a thermometer and you want to use a certain liquid, that liquid, should it have high specific heat capacity or low specific heat capacity? Should that liquid have high coefficient of volume expansion? Should it have low coefficient of volume expansion? And they'll make up four options like that: high, 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 low, low, high, and low, low. So what would be the answer? What do you guys think? Think, take 30, 40 seconds. The liquid which you use in a thermometer, should it have high specific heat capacity? Should it have high coefficient of volume expansion? Or should it have low? What? Let me ask you this thing. Do you want the temperature to change fast or slow? When you put the thermometer in your mouth, do you want to keep the thermometer for 5 seconds or 5 hours? Do you want the thermometer to react fast or react slow? You want it to react fast, right? That means even for a small amount of heat, you want the temperature of the liquid to change. Do you agree with that? So when you put it in your mouth, it is taking heat from your mouth. That's a very small amount of heat. So if your specific heat capacity is high, what will happen? It will take a lot of time for the temperature to change. So you have to keep the thermometer in your mouth for hours. You don't want that. So now you tell me, should you have high specific heat capacity or low specific heat capacity? You want the liquid to change temperature fast or slow? You want it to change fast. That means you should have low specific heat capacity. So temperature should change even for a small amount of heat. Next thing, chalo, temperature changed by 1 degree, right? Do you want the liquid to expand more or liquid to expand less? Again, think about thermometer. So in the thermometer, you have the bulb here. If you have a very low gamma, means what? If you have a very low gamma, means for every 1 degree, you will expand very little. So you will only expand this much. But if you have high gamma, then you will expand more. Which is more visible, the small one or the big one? Do you want to get a big reading or a small reading? You want to get a big reading, right? So that it is more visible. So you want the liquid to expand easily, right? So you should have high gamma. Because what is coefficient of volume expansion? Higher the coefficient of volume expansion, more easily liquid can expand. High coefficient of volume expansion. So gamma tells you how easily liquid can expand. Specifically, it will tell you how difficult it is to change the temperature. So liquid expands more for a small temperature change. So when you put it in your mouth, temperature change will be 3 to 4 degrees. So you should move sufficiently large enough for you to observe it. If it moves only 1 millimeter, your eyes can't even figure out it moved. So when you keep it in your mouth, it should absorb the heat and it should be able to raise the temperature fast. So it should have low specific heat and high gamma. This will make you a more sensitive thermometer. What do you mean by sensitive? Sensitive meaning it responds for small changes. Did you ever see this thing? You will say, yeah, this person is very sensitive. There is a person there, you call him pig and they start feeling bad about it. There are some people you call him pig, donkey, everything. They're like, bullshit. They don't even care. So we say, yeah, boss, this guy is very sensitive. Or if you see kids, right? If you pinch their skin, it becomes very red. They are very sensitive. So you want the thermometer to be sensitive. It should detect small changes. Clear with this? So that is how they can frame a theoretical question on this one. Coefficient of volume expansion and specific heat capacity. Yeah, low S and high gamma. Right, Aditi. Right, Samik. Yeah, most of you did get it. All clear with this? So that is how they can frame a theoretical question on this. Okay, great. Let's go ahead with the questions then. So again, remember the only thing I taught you, dq is msdt. You kept a rod here. Mass m, length L, alpha, which is coefficient of linear expansion. S, the specific heat capacity. Then someone gave heat Q to the rod. Find the change in temperature of the rod when a heat Q is given. Assume all the heat is retained by the rod, okay? So there is no heat escaping or anything. Assume all heat is retained by the rod and neglect any elastic potential energies. If they don't mention, you can ignore it. It's a good question. I made it up. The actual question was this, huh? This thing came in JEE Advance. I don't remember the year, but a very old one. The question was this. You have two solid spheres. One solid sphere is on the ground and one solid sphere is hanging from the ceiling at the center. Both are identical. Two identical solid spheres. Same mass, same density, everything same, but one is on the floor and one is hanging on the ceiling. Both are given same amount of heat. Which ball will have more temperature, ball A or ball B? This was an actually J advanced question. You gave same heat, same body, everything same. The only difference, one is on the ground and one is on the ceiling. So based on this, I made it up. So if you got this, you will get that also. So what is the catch? Think about it. Take a minute or two. It's a good question. So what's the question? What is the catch? How do you handle it? Remember the formula dq is equal to ms dt. Whenever I give you a dq heat, temperature will change by dt. So okay, what do you guys think about this question? Let's start from here and then we'll go there. The ball on the ground and the ball which is hanging on the from the ceiling, which is hinged at the center. When you give same heat, one thing is clear: they'll have different temperatures. Why? What changed? What is so different between them? If they're identical, they have same heat, then there is no heat loss. Okay, the heat is not going to the ground or something. Nothing. All the heat is retained by the body. Which body will have more temperature? That was the straightforward question in advance. It was pretty old one, I think 20-year-old PYQ, I guess. Yeah. The catch was this. Listen, when you increase the temperature, the body is going to expand. When the body expands, this ball here will become like this. Whereas this ball here will expand like this. Did you notice something? So what happens? If you expand like this, what happens? Look at the center of mass. The ball on the ground, the center of mass has actually gone up. Whereas for the ball on the ceiling, the center of mass is at the same position. In this case, the center of mass goes up. That means some of the heat energy is used to increase the gravitational potential energy of the ball. Are you getting this? All the heat energy is not used to increase the temperature. Some of the energy was used to increase the potential energy of the ball. So here Q will be mg delta H center of mass plus ms delta T. This is for ball A. Whereas for this thing, Q is equal to ms delta B because the center of mass will still remain at the center. Are you clear with this? So that was the trap that there's a concept they're using. The ball on the ground, when it expands, it will push the ground, it will go up. So the center of mass will rise a little. Where did you get that energy from? It must have come from heat only, right? So some of the heat energy got converted into gravitational potential energy. Therefore, temperature at B is greater than temperature at A. That was the answer for that thing. All got the thing? Now, using the same logic, can you try this now? I made a numerical out of it, but that was actual question. Who will have more temperature? Get this, I'll give you a minute now. They were using thermal expansion, work power energy, and calorimetry. How to do this thing? See. So let the temperature increase by delta T. So initially the rod was like this. Then the rod becomes like this. So initially this length was L. This was the center of mass. This was the temperature T. This was the temperature T plus dt. So here your center of mass is at a height of L by 2. Now your center of mass will go slightly up. That will be L by 2 into 1 plus alpha delta T. Make sense? So when you give the temperature, the rod will expand, and because of that, it will push the center of mass slightly upward. So whatever energy you give, heat Q, is used for two things, ms delta T. So remember that ms delta T is the heat required to change the temperature, plus mg delta H center of mass. So this heat is used to change the temperature. So don't blindly remember Q is equal to ms delta T. Try to understand the meaning of that. The heat required to change the temperature is ms delta T. Now, whatever total heat that I gave, in that some of it is used to change the temperature. The remaining is used to increase the gravitational potential energy. So then we get Q is equal to ms delta T. And delta H is nothing but the change in position, which is L by 2 alpha delta T. You're done. I think once you know what to do, it is pretty straightforward, but you should get an idea that the center of mass is moving. Check. Clear with this? So keeping a rod vertically and keeping a rod horizontally will change the whole question. Any doubts on this? Clear, na? Obvious? Shaurya? Vanshika? Clear with this? Vedika? Rudransh? Clear. Great. Next one. We got a rod here. We got two springs. K1, K2, rod mass M, length L, alpha, S is the specific heat. Springs are in natural length. This is the top view. There's no gravity. You gave heat Q to the rod. Find the change in temperature and the compression in the springs. Again, same story. You give heat to the rod ka temperature will change and the rod will expand, the springs will get compressed. Find the change in temperature and the compression in the springs. Assume no elastic energy in the rod. Logically speaking, the rod will actually feel it got compressed. We are ignoring it. We can actually include that also and solve, but okay. Just becomes a little lengthy. Let's get this. So we got a rod connected with two springs, and you have a heat Q. It's on a smooth floor, so there's no gravity. Just get me the equations. Solving is a little lengthy, but get me the equations. That is one. Got the equations right. Try, I'll give another 30, 40 seconds. Okay, let's see. Right, Samyak. You need one more equation though. So when this rod expands, so initially the length was L. Okay. Temperature was T. Now when the rod expands, this becomes L into 1 plus alpha delta T. That means this spring must have got compressed by x1, this spring must have got compressed by x2. Now we don't know, let's call it x1 and x2. Since the total length is constant, can I say like this? So x1 plus x2 must be equal to the change in length of the rod, which is L alpha delta T. Do you guys agree with that statement? Whatever the rod must have expanded, that must have gone into the springs. And I don't know how much the springs have got expanded, but yeah, that is there. Now, second thing, since the rod is in equilibrium, the springs are pushing with equal force K2 X2, and this spring is pushing with K1 X1. Since the rod is at rest, K1 X1 is equal to K2 X2. This is your second equation, everyone. This is your first equation. How many variables are there? You have x1, you have x2, and x2 delta t. You have three variables. I need three equations. What is the third equation? Energy conservation. So whatever heat you are giving, it is going into the spring of k1 x1 square. It is going into the second spring of k2 x2 square. And then the remaining energy is becoming heat ms delta t. That's your third equation. Please check. If you got the three equations, you can solve. Let the springs compress by x1 and x2. There is no guarantee they'll be equal. K1 x1 is equal to K2 x2. That is a relation between x1 and x2. Third, whatever heat you gave, some must have gone into the springs and the remaining must have used to increase the temperature by delta T. And others, do keep your cams on. Arya, Shaunak, Utsa, cams on. Clear with this? So this is how you can play around with this. That ms delta T, it is just not that. You can bring your mechanics, energy, everything. Any doubts on this? You can make the question more tough by even putting Young's modulus. Then you'll even get elastic potential energy. That becomes a little lengthy, but yeah, can be done. All clear with this? Shreyansh? Clear? Sudiksha? Shreyan? Pratyasha? Aditi? Got? Great. Let's go ahead. A little more theory. We have something called heat capacity. Be careful, not specific heat capacity, heat capacity. The symbol is H. Now, this is again mostly used in labs actually. We don't expect, right? Someone who will go to the lab, he will know what is the mass of the body, what is the specific heat of the body, and all. So, what they do for simplicity, on top of the body, they'll simply print something called heat capacity. So, heat capacity is simply the amount of heat required to change the temperature. Example, let's say you will have a body like this. So, on the body, it will be written like this: H is equal to 300 calories per Celsius. Meaning, if we give 600 calories, temperature will change by 2 degrees. That's it. I don't care what is the mass of the body. I don't care what is the, you know, anything. It is just you give this much heat, temperature will change this much, and you're done. So how do we calculate this heat capacity? So dq is equal to ms dt. This is written as h into dt. So there. So heat capacity is nothing but mass into specific heat capacity. Again, it is mostly to do with the lab ka thing. So be careful with that word. Huh? I have seen questions on this in statements especially. Heat capacity, specific heat capacity. Specific heat capacity is independent of mass. Because what is specific heat capacity? The amount of heat required per unit mass per unit degree. So whether you take 1 kg or 10 kg, S will remain same. It's like your density. Density of 1 kg water or 10 kg water is same. But volume of 1 kg water and 10 kg water is different. So specific heat capacity is independent of mass. It depends only on the nature of the material. Whereas the heat capacity depends on the mass because heat capacity is m into specific heat capacity. I think in one of the JE question, they gave heat capacity is equal to some 200 and they gave mass of the body is some 2 kg. What most people did, they took this as m and they took this as s and they multiplied 2 into 200 and they got the answer. They got some 400. But the thing is, when you give heat capacity, I don't care about the mass. Answer was 200 only. You're getting it. So it was a small trap, but yeah, people, when they don't notice it, it can be a simple mistake. So be careful. Specific heat capacity and heat capacity are two different things. If I have to give an example, let's say specific heat capacity will be 100 calorie or a gram per Celsius. If you have a 20-gram body, the heat capacity is m into s. That would be 2000 calorie per Celsius. Did you see the mass term is missing there? Meaning for that body, for that particular body, if you give 2000 calories, it will change the temperature by 1 degree. So mass is multiplied there. So if you increase the mass, heat capacity will change, but S will not care about the mass. Clear with this? Again, just a theoretical thing, not really that conceptually great, but yeah, there have been questions on this where people got trapped. They didn't read the word heat capacity and specific heat capacity properly. All clear with this? Next one. There is again one more theoretical thing. Now again, whenever you go to a lab, right, you'll observe most of the time people are actually, boiling water and doing experiments on water. Then people realized, when you're heating a container with water, even the container is also absorbing heat. So they said, yeah, let's make this more easy. So we define something called water equivalent. The amount of water which gives you the same temperature change as the body for same heat. Meaning, let's say you have a container. Now, the problem was this. If you take a container and if you have water inside, when you give heat, all the heat is not absorbed by the container. It is absorbed by the water and container. So you get actually an error. So what these people did, they took this container and they gave some heat and they saw what was the temperature change. So on top of it, it will be printed something like this. Water equivalent is 50 grams. The meaning of this is, if you replace this container with 50 grams of water, and if you give heat Q to that water, you will observe they'll have same temperature difference. So it is a way of converting a container into in terms of water. Again, this also has to do with the lab ka thing. So let me show you an example. So we have a container filled with water. So inside the container, we have 100 grams of water. And it will be written on the container, water equivalent is 20 grams. Or let's say 80 grams. Now, technically speaking, when I give heat Q, this is how we should write the equation as. So heat Q will be mass of the container, specific heat of the container, delta T, plus mass of the water, specific heat of the water into delta T. This is how you should write the equation. But can you see the problem there? You need to find what is the mass of the container, you need to find specific heat of the container, what material. So if instead of all that, you can just replace this whole thing with 180 grams of water and you can solve the problem. You can simply say Q is equal to ms delta T, where this is 180 grams of water. This is specific heat of water. So the person who's doing the experiment need not care what is the mass of the container, whether it is made of copper, whether it is made of aluminium. Yeah, we can just finish off with that. All clear with what is water equivalent? So exam the question will be like that only. We have a container with 100 grams of water and the water equivalent is of 80 grams. A heat of some 200 calories is given. Find the change in temperature. So you can treat the whole thing as 180 grams of water and solve the problem. Next one. Clear with this? Bit of a theory there. Clear na, Ashmi? Arya? Next thing. Latent heat of fusion. The symbol is LF. It is the amount of heat required to melt one unit of solid into liquid. So Q is equal to M into LF. So whenever you are converting solid to liquid, phase change basically, we use this formula. We don't use ms delta T. Again, you have to remember the value here. Example, latent heat of fusion of ice. So to melt 1 gram of ice, you need 80 calories. So someone heard about this thing and they came up with a diet called ice diet. So this thing, what you do in this diet, right? Morning breakfast, you eat ice cubes. In the lunch, you eat ice cubes. In the dinner, you eat ice cubes. So for better taste, you can put a little lemon and salt. So this, so this is a diet with a negative calories. First of all, you're not getting any calories. On top of it, you're using your body ka heat to melt the ice, so you burn more calories. Now, but just let's try to calculate this thing. How hopeless is this? Now, you know your Dairy Milk Silk, the big one, the 125 grams wala. If you open that anytime, observe that 100 grams of Dairy Milk Silk will be around 550 calories. Right. So if you eat that full dairy milk, 125 grams, simplicity, let's take it as 600 calories. Now be careful again. This 600 calories is not calories, it is 600 kilocalories. You're getting it? So when you're eating some stuff, the label when it is written, it is not actually calories, it is kilocalories. Clear with that? But they will write it as calories, so that I don't know why they write it as calories, but all the units you see is actually kilocalories. Okay? So you have eaten one dairy milk, 600 kilocalories, and you want to use ice to melt that body ka whatever calories. Let's see how much ice you have to eat. So 600 kilocalories is 600 into 80 calories by you are burning 80 calories, 600 kilocalories, right? 60 into 10 power 3 calories. And you're going to burn 80 calories per gram. Calorie will go off, gram will come up. That will be 60 by 8 into 10 power 3 grams. 10 power 3 grams is 1 kg. So 4 twos are 4 15s are. That is 7.5 kgs of ice cubes. If you eat 7.5 kgs of ice, then it is equal to melting 600 kilocalories. It's a very bad diet. First thing, what happens when you eat so much ice, your body will start using this internal energy, and what happens, right? Your immunity actually starts dropping. You actually become sick. So never try this thing. But next time when you're eating an ice cream, you can tell yourself, Dekho, I'm burning calories by eating ice cream, and you can comfort yourself. So at least you can stop feeling little guilty. But there, so someone actually came up with that thing called an ice diet, and they did it also. But people started falling sick after 2 3 days. Did you ever eat in a lot of ice cream? You'll get a brain freeze. Ever happened to you? IIT में ना, we have something called an ice cream party. Every semester they keep one day evening, right? It is unlimited ice cream and unlimited jalebi. It used to happen in our hostel. Getting it? So during that day, right, we literally used to skip breakfast and lunch just to eat ice cream in the evening. So I still remember in my first semester, right, it is an ice cream party, 6 different flavors, unlimited ice cream. I ate 17 scoops. The record was 32 though. So people were counting how much. After eating 17, my brain literally froze, you know. I was just wandering around there in the corner. I was like, I was not understanding anything. I was getting a headache. I was like gone completely. Uh, you got a brain freeze, big, big scoops. Right? So when you're people were fighting and jumping and eating and everything, and they had a lot of ice cream to eat. So all our first years, na, so we are fighting for the ice cream. And then after some time, right, someone came and told me, take this box and deliver it to room number 313 or something. I said, deliver the ice cream? I said, fourth year stays there. Fourth years don't come down. Fourth years are like the senior most retired people in the hostel. So for them, you take the box. So I and another 4 people, right, we have taken 25-liter ka boxes. एक box होता है 25 liters का ice cream. We have taken 6 boxes, 6 different flavors to the third floor. All the fourth years are there sitting with a scoop and they're eating ice cream there. They looked at us and said, you want to eat? I said, okay, you also sit. And they gave us a spoon and we're eating it from the 25-liter ka tub. It was fun. So we used to have the ice cream party. You'll get something called a brain freeze. You should try, but I think you should eat around 10 to 12 scoops before getting it. Next thing, latent rate of vaporization. This we give LV. This is the amount of heat required to vaporize 1 gram of liquid into gaseous state. Arya, are you there? Not there.
Yes.
Okay. Heat required to vaporize 1 liquid to a gas. So be careful here. During a phase change, the temperature will not change. This is M into LV. So there is a question like this in one other thing. If heat is given to the body, should the temperature change? Not necessary. If heat is given to the body, there is a possibility you're using this heat to, vaporize or melt the substance. So latent of vaporization of water is 540 calories per gram. This is a pretty large value. So you know why when there is a fire, people put water? Why do you put water to stop the fire? Ever thought about it? Because it is cheap, abundant. So
It
water
puts
has
out the
this.
fire.
It puts out the fire. How? So what actually happens, right? When a building is on fire, most people think, you know what? It cuts off the oxygen supply. Not true, actually. To cut off the oxygen supply, you literally have to drown the building in the water. So what happens is when you take something, a wooden material, right? A wood has an ignition temperature of 800 degrees. So if you just take wood and put something in it, won't burn automatically. You need a temperature of 800 degrees for the wood to burn. So when you put a lot of water, what happens? The heat will be absorbed by the water and the temperature goes below 800 degrees. So the wood which is burning will continue to burn. Maybe it might stop, if you put enough water. But the new wood will not catch any more fire. So, and the water has this very special property. 540 calories per gram is huge. It's really a big one. It happened with me once. Uh, you know this thing? We have this heater. You have this immersion rod. Ever seen this? Nowadays, I think everyone has geysers, but we have something called an immersion rod. Ever used it? So this immersion rod, right? You have the bucket. So when I used to stay in the hostel, when you want hot water, this is one of the things. We used to put that immersion rod in the bucket and leave it there for some 20-25 minutes and you get hot water. So one day what happened? I wanted some hot water. So I took a bucket, filled it with water, kept the immersion rod inside. And then I went down to get some, stuff. I went to the general stores and I was getting some soap or something. I don't remember. I went down. I thought, okay, I'll go down and come back in 10 minutes. So water boil ho jayega. I went down and I met one of my friends. He said, Arun, kya kar raha hai? I said, nothing much. I said, you want to go for a movie? I said, let's go. So I just got into the auto and went to the movie. Went to the movie, had some food also. Then we are coming back. And while coming back, night, something was poking me. Something was clicking. Yeah, kuch to bol raha hu, kuch to bol raha hu. Something was, I forgot. Then suddenly it hit me. Shit, Ray, kept an immersion rod in the house and I came. It has been 4.5 hours till then. And I was so scared. I was like expecting, yeah, pura house jal gaya hoga. There must be a fire engine outside the house. I was assuming every nonsense thing. I came home running, got down from the auto, ran to the room, opened the door, and I saw, and bucket mein half of the water was missing. Yeah, bucket ka handle got melted, but only half of the water was missing, and the house was not on fire. And then I realized, bloody, it is very difficult to vaporize water. I mean, just think about this. This immersion rod which we use, right, is around 2 kilowatts, right? 2 kilowatt method, that is around 2000 joules per second. So 2000 joules divided by 4 calories will give you roughly around 500 calories per second. Even if you assume 500, like 540, round it off, that means every second you are vaporizing only 1 gram of water. That is a 25 kgs ka bucket. Matlab 25 liters of water is there inside. That would take around 25,000 seconds to vaporize that entire water in the bucket. Again, neglecting all vaporization and everything. Right? And 1 hour has 3,600 seconds. Right? So, yeah, that is 250 by 36. That will still come to around like what, maybe 7 to 8 hours. So, we are kind of safe actually. So next time when you see this, thermal power plants, you'll understand how much coal they burn to actually generate that steam. It requires a hell lot of energy. If you touch that, you'll get a good shock. That is it. All clear with this? Latent heat of vaporization and latent heat of fusion. So let me give an example. Whenever you are heating up a liquid, how does it actually change? So this is important. Listen carefully. So a solid will become liquid. Liquid becomes gas. So this conversion is called phase change. Now, consider we have a solid and you're giving heat continuously. Let's say how this thing will work. Consider a solid is heated at a constant rate. Okay, so see, when you take a solid block and when you are heating it, remember solid you have molecules which are vibrating. So basically you have a lattice there. You are giving heat to the body. So what will the body do? It will take all this energy and it will use to increase the kinetic energy of the molecules. So the molecules will vibrate more rapidly, therefore temperature increases. That's the definition of temperature: random molecular kinetic energy. So it will still remain solid. So when you heat a solid object, it will still remain a solid. Temperature rises. Kinetic energy of the molecules increase. The potential energy of the molecules remain constant. What is the potential energy? It is the bond energy between them. It does change a bit. We can ignore it compared to the kinetic energy. If you continue to give more and more energy, now what will happen? These molecules are vibrating so strongly, some of them will start breaking the bonds. So you'll get partially some liquid and some solid. So we get a solid and a liquid mixture. So that means during this process, temperature will remain constant. So all the energy that you're providing is used to break the bonds. So that was the question. If heat is given to the body, should the temperature increase? Not necessary. So whatever heat you're providing is used to break the bonds. So that is the reason potential energy will increase. So this is what happens when you are heating the material continuously. Now you continue to heat the material, the whole substance will become liquid. The phase change is complete. Now understand one thing, temperature will not increase until and unless each and every bond breaks. Then you continue to heat more. The liquid will remain in the liquid state, but temperature will increase. Think of like this: 0 degree water becomes 100-degree water. It is still water only, but temperature has increased. Again, same story, temperature increases, kinetic energy increases, and potential energy is constant. You continue to give more energy. Now the bonds will start breaking again. You have some liquid and you have some steam. So again, phase change is happening. Again, same story. Temperature is constant. So until unless all the liquid molecules will break and become vapor, temperature is not going to rise. So there. So we can write a statement here. If heat is given to the body, temperature may or may not rise. So keep that in mind. General misconception. If heat is given, people think temperature rises. Not necessary. There can be phase change. If heat is given, temperature may or may not rise. Let's put this on a graph. Now, this is a phase change graph. This graph is important. They do ask a lot on this. So if you plot this graph on a temperature versus time graph, so I'm starting from here. Maybe that need not be 0 there. So I can start the graph somewhere here. So how will the graph look like? Initially, temperature will increase. Remember, solid is still solid, but temperature is increasing. Then solid will start melting, temperature will remain constant. Solid will become liquid, temperature will rise, liquid will become gas, temperature remains constant, everything becomes gas. So this is how the graph looks. So this is O, A, this is a solid state. A, B, this is a solid and a liquid mixture. B to C, everything has become liquid. C to D, again phase change. You're on the liquid and a gas ka phase change. So whenever there's a phase change, temperature remains constant. This is a gas ka again. Now, if you look at this, there is some good data points here. Assume heat is given at a constant rate. P calories per second. So look at the formula there. Q is equal to dq is equal to ms dt. Divide both sides by time. Dq by dt is equal to ms and dt by dt. This is nothing but P. So dt by dt, rate of change of temperature, is ms by P. P by ms. Remember, this is your slope. Slope is proportional to 1 by ms. Quite an important thing. That means in this graph, if you look at the line of OA, the slope of the line OA is proportional to 1 by mass of the body and specific heat of the solid. Understand the meaning of this. So if there are two objects, they did ask question like this. There are two objects, S1 and S2. Which one is bigger? The one with the more specific heat will have lesser slope, isn't it? It's more difficult to change the temperature. Others, do keep your cams on. Not sure why you guys are keeping your cams off. Arya, I have to keep telling you 10 times. Kya?
Sir, I have net issues.
So when will you tell me this? After kicking you out for 4 times? You have a problem. You should tell me when the class starts. If you tell me after the class starts, I'll think you're just giving an excuse. So when you go from B to C, if you see that specific heat is for the liquid. This is 1 into m into specific heat of the gas. There. So that each line will tell you the slope is for different substances. Similarly, what does that length AB tell you? Understand the meaning of this AB. A to B is a phase change. So the longer the length means more time it took to melt the solid to ice. So the length AB is proportional to latent heat of fusion. The longer the length, meaning more time you took. Why did you take more time? Because it was more difficult to melt. The length CD is proportional to latent heat of vaporization. So more time indicates you require more heat to melt. I know there's a bit of a theory there, but quite an important graph. So looking at the graph, you can compare actually two different materials ka specific heat and latent heats. Have a look at the graph. Clear with this? And one more last theoretical point here, principle of calorimetry. This is same as the work energy theorem. It is another form of conservation of energy. So what it simply says is heat lost by a body must be equal to the heat gained by the other bodies. Heat is also a form of energy, right? So it has to be conserved. So in an isolated system, if the heat is not coming in or not going out, the total heat must be zero. The net heat gained or lost is same. There, that's your entire theory of calorimetry. We'll take a small break and then we'll do the problems. But this graph is quite important. So any doubts on this? Clear? Take a break. Come back by 9:40. We'll continue from here. Go wash your face, everyone. Some of you are really sleepy and tired for some reason. Come back in 5 minutes. Let's start off, everyone. Okay, let's see a question. Cams on, everyone. This is a graph between temperature and time. This is material 1. This is material 2. So just looking at this graph, I want you to compare So for the solid substance, compare the specific heat capacity S1, S2, compare the latent heat of fusion L1, L2, compare the specific heat of the liquid S1, S2, latent heat of vaporization L1, L2, and for the gas again S1, S2. There. So you just start telling whether they're equal, greater than, or less than. Let's get this everyone. You can have a look at this once in case you forgot. So higher the specific heat capacity, lesser the slope. Meaning, think about it logically. What do you mean by higher specific heat capacity? It is more difficult to change the temperature. That means you require to give more heat or you have to give more time to change the temperature. So slope will be obviously lesser. So looking at these two graphs, you have to tell me which one is greater and which one is lesser. Get this. It's a small chapter. Calorimetry we will be done with today. Then we'll start with KTG, which is same as your gas loss. Let's see. So how do you compare this? Remember, you can clearly see the slope of OA is greater than slope of OA1 is greater than slope of OA2. So if your slope is more, then your specific heat capacity is less. So S2 is less than S1. Between ABs, which AB is bigger? The green ka AB is bigger. So L2 is greater than L1. Between BC, the red ka slope is smaller. S1 greater than S2. That's it. You just have to compare this. So this is greater and clear with this? Any doubts on this? We just have to keep checking for the slopes and the lengths of the AB line. Yeah, less than, greater than, less than. Yeah, perfect, Thamik. Right, Aditi? Any doubts on this? All clear with this? There have been a lot of questions on this, the graph. So be careful with that. Devanshi, got this? Tanishka? Shaurya? Shaunak? Clear with this? Great. Let's see one more. We have an ice block. We have 100 grams of ice at minus 50 degrees. How much heat is required to convert this into 200 degree ka steam? How much heat is required to vaporize it 200 degree steam? In case you don't remember the value, specific heat of water, 1 gram per 1 calorie per gram. This, if you're an ICSE, right, you have done something like this in school. Specific heat of ice and specific heat of steam is half calorie per gram per degree. Latent of fusion of ice is 80 calorie per gram. There, let's get this. So how much heat do you require to melt this ice into, you have to make it into steam of 200 degrees. Get this. Let's see how you handle this. Seven, nine. Yeah, that looks right, Samyak. Others, try. I'll give you a minute. Yeah, it is little lengthy calculation. Let's see. See. Right, Aditi. You have two answers. So you have to be careful. Directly, you can't make ice into steam. It goes through the stages like which I showed you. So let's see. So first thing, you have 100 grams of ice at minus 50 degrees. You directly cannot become steam. So first, this will become 100 grams of ice at 0 degrees. Then this will become 0 degree water. Then this will become 100 degree water. So you have to go stage by stage. You directly can't jump. Then you become 100 degree steam. Then you become 200 degree steam. So each stage will require a certain amount of heat. Hope you're clear with this. So let's calculate. So first thing, when you want to go from -50 to 0 degrees, remember you are still a solid. Getting it? You're not doing a phase change. Your temperature is changing. So we use the formula Q is equal to ms delta T. M is 100, specific heat of ice is half, and delta T is 50. That's 2500 calories. You require this much heat to convert ice from -50 to 0. Right, Utsa, you also got it. Then you're converting ice into water. Now see, when you're converting 0 degree ice to 0 degree water, temperature is not changing, but substance is changing. This is a phase change. The formula is Q is equal to M into L fusion. That's it. Just be careful. Don't blindly use ms delta T every time. You need to check whether temperature is changing or there's a phase change. Right, Anvita? You got it. So this would be 100 and the latent rate of fusion is 80. That would be 8,000 calories to melt the ice. Then you're converting water to 100 degrees water. Again, that is equal to ms delta T. That is 100. Specific heat of water is 1 and this is 100. That is 10,000 calories. Here you're converting 100-degree water to steam. Again, phase change, M into LV. That would be 54,000 calories. This is the big one. Here again, Q is equal to 100 into specific heat of steam is half into 100. That's another 5,000 calories. Add up all of this. That's 2,500, 8,000, 18,000, 64, 872, 72, 577, 79,500 calories. Please check. Again, not a tough thing, but most people don't realize, like, you directly can't jump from, ice to steam. You have to go through each phase change. Please have a look at this. All clear with this? Easy. Great. Let's see a few more. There, let's get these two. Let's see. What was the first one? A metal block absorbs 4,500 calories of heat. Its thermal capacity. So basically, this is your heat capacity, everyone. So this is a straightforward one. So Q is equal to ms delta T. This ms is your heat capacity. So you're done. So it's 4,500 heat capacity into 80 minus 30 is 50. 90 calorie per Celsius. That's an easy one. What about the B part? Right, Samyak. Right, Utsa. Right, Anita. Read the question. Two beakers A and B containing liquids 300 and 420. The amount of heat on them is equal. Technically, they should say internal energy, but okay. Q is equal to MA, SA, temperature at A is equal to, we are saying MA, MB, SB, TB. 300.8 TA, 420.6 TB. So TA by TB will be, how much is this? Four twenty into 6 by 300 into 8. 0, 0, 6, 5, 42. That's 21 by 20. You can clearly see since TA is greater than TB, heat flows from A to B. Easy. Remember the definition of heat. Heat is it flows from higher to lower temperature. It does not flow from more heat to less heat. It flows from more temperature to low temperature. Clear for this? Right, Rudransh. Right, Devanshi. Got it. It's an easy one. Let's see the next one. Let's get this. Three liquids ABC, temperature 10, 25, 40. When A and B are mixed, temperature is 15. When B and C are mixed, temperature is 30. When A and C are mixed, what is the temperature? The liquids have same mass, but they're not same liquids, huh? So specific heats are not same. So let's see how will you get this. Try. Everyone should try. I'll show you. See. So when you mix A and B, temperature is 15 degrees. So let's start like this. Let's take A and B. It is easy to see here when you mix A and B, A is going to gain heat and B is going to lose heat because A ka temperature is 10 and B ka 25. So can I write like this? Heat gained by A is heat lost by B. So mass is same, M into specific heat of A. So what is A ka final temperature? 15. What was initial temperature? 10 because you gained final minus initial here. This is heat lost, so initial temperature must be more, M into SB. Your initial temperature was 25 and this is 15. So we get SA is equal to 2 SB. Right, Anvita, you got it. Clear with this. So that is for AB. Now when you do for B and C, same story. The heat lost by B, M into SB into your final temperature is 30. So you gained heat from 25 to 30. Whereas C lost heat from 40 to 25. 25 or 30, sorry. There. So we get SB is equal to 2SC. Great. Now when you do the same thing for A and C, M into SA. Now I don't know the final temperature. Let it be T. A ka temperature is 10. This is SC and this is 40 minus T. See, so the one who is gaining heat, right, the final temperature will be more than initial. The one who is losing will have initial temperature more than final. You're done. So take SA from here, substitute here, take SC from here and substitute here. This would be 2SB T minus 10 and this will be SB by 2, 40 minus T. SB will cancel. We end up with T is equal to 16 degrees. First option. Please have a look at this. And others do keep your cams on. Easy. That's a proper mains level question. Any doubts on this? Clear, na, Vanshika? Vedika, got this? Shriyansh? Rudransh? Devanshi? Tanishka? Utsa, clear with this? Let's see one more. Let's say we have n different liquids. If you have n liquids of mass M1, M2, M3, so on till Mn, specific heat capacity S1, S2, S3, so on till Sn, temperature T1, T2, T3, so on till Tn, meaning all the liquids have different mass and different specific heat capacity and different temperature. They are mixed. Find the final temperature of the mixture. This is a good one. We don't know who is bigger, who is smaller. So how do you handle this? This will actually give you a general formula also when you mix liquids more than two of them. If you mix two liquids, it is easy to see. One will lose and one will gain. But if you mix n liquids, I'm not sure who is going to gain and who is going to lose. Think, take a minute. Right, Samyak. One answer. Others? Okay, let's see. Right, Shriyant. Now, again, what is the problem we are facing here? The problem here is you're not sure who is gaining heat and who is losing heat, right? So whenever you have the problem, now start like this. Assume all are gaining heat or assume all are losing heat. It doesn't matter. The science will take care of it. So let the final temperature be T. Let the final temperature be T and let all gain heat. Let's assume and see what happens. If all are gaining heat, that means then the heat gained by the first liquid, M1, S1, T final minus T1. The heat gained by the second liquid, M2, S2, T final minus T2, and so on. The liquid Mn, Sn, T final minus Tn. But tell me something, can all the liquids gain heat? When you mix all the N liquids, is there any heat entering from outside or heat leaving from outside? So the net heat flow is zero. The net heat is zero. Is that making sense? When you mix the N liquids, this is a system. There is no heat coming from inside. There's no heat going from, coming from outside or going from inside. Therefore, this will be M1S1 plus M2S2, so on until MnSn T minus M1S1 T1 plus M2S2 T2, MnSn Tn is equal to 0. There. So we get T is equal to sigma Mi Si Ti by sigma Mi Si. Now in this equation, there will be some temperatures which are greater than T, some temperatures less than T. So the signs will automatically take care of them. Some of them will become negative here. Clear with this? So when you're not sure who is gaining heat and who is absorbing heat, just assume everyone is gaining heat. The signs will take care of themselves. Is this clear, everyone? Have a look at this. Please ask me if you're confused. All clear with this? Next one. Clear, na, Advai? Advai, clear with this? Advai, are you there? Advai? Next thing. Please do respond when I call your name. Not sure why is Adke playing with his hair. Anyways. Next one. 100 grams of ice. This is a good one. Huh? In calorimetry, this is one important. Good questions. This is mixed with 100 grams of water. At 70 degrees. Find the final temperature and the composition of the mixture. Composition meaning you have to tell me how much ice is there and how much water is there. Or if everything is water or if everything is ice. Advai, are you there? Advai, are you there? Yes, no, say something, nod your head. I was calling your name so many times, you're not responding at all. You're busy playing with your hair. Are you there? You're still not there. Hello. This guy's okay. Let's get this. There's a B part and C part also for this. You're mixing 100 grams of ice at minus 20 and you're mixing with 100 grams of water at 70. When you mix them, how do you get the final temperature? Now, this is important. You can't use the previous formula. In the previous formula, if you observe, there was no phase change. Everything was ms delta T. Here, The ice is melting, so there's a latent heat also. So how do you handle this? Take a minute, then I'll show you. Think. How will you handle this? This is a pretty good one, mixing of ice and water and all that stuff. Okay. Don't remember the answer, but Shreyansh says finally 133 grams of water remaining is ice. Let's see, anyone else got it. 175-gram water and 25-gram ice. Some got something else. You have two different answers. Okay, let me show you one model, then I'll ask you. Now, the problem here, you know what? I'm not sure when the ice is melting, did the entire ice melt or did some ice left over? What exactly happened? So that was the confusion here. So how do we go about it? So this is what we do. We start with a common state. So you're saying 100 grams of ice at minus 20 degrees. Okay. So listen carefully. I'll show you one model. We have 100 grams of ice at minus 20 degrees and we have 100 grams of water at 70 degrees. Now, since I don't know exactly how it looks finally, we will always start with an assumption. Assume a common state. I will assume everything has become 0-degree water. Why 0-degree water? Nothing. I'm just taking anything randomly. You can choose anything you want. You can take 10-degree water also. Assume a common state. This is just like, the two block problems in friction. When we don't know whether the blocks are going together or slipping, what did we do? We started with an assumption, right? Let everything go together. So if this is your common state, let's ask this thing. So for the ice to become here, what should happen? First, it will become 100 grams ice at 0 degrees. Remember, you cannot become water directly. Then you become water. So how much heat is required for this? So when 100 grams of ice from minus 20 becomes 0, the heat required will be 100. Specific heat of ice is half and 20. That would be 1000 calories. So you require 1000 calories to convert ice from minus 20 to 0 degrees. Then ice is melting from ice to water. Q is equal to M into LF. That would be 100 into 80. That is 8000 calories. That means for this guy to become water, someone has to provide 9000 calories. Is that making sense? Now for this guy to become water, it has to cool down. So Q is equal to MS delta T. This is 100. This is 1 into 70. So we got 7000 calories of heat will be released. When you're cooling down water, it releases heat. Now, finally, what do you have? Since you assumed everything has become water, I have 200 grams of water. See, I'm changing the whole question now. I have 200 grams of water at 0 degrees. And how much heat do I have? This thing has released 7000 calories. And this thing has absorbed 1000 calories and 8000 calories. That means I have a deficit of 2000 calories. So can I ask you a new question? I have 200 grams of water at 0 degrees and someone removed 2000 calories of heat. What will happen? Isn't that how the question has become? Now, instead of mixing and everything, you converted the question into something more easy. So if you remove heat from the water, it starts freezing. Since heat is negative, the water freezes to ice. How much? Q is equal to MLF. So Q is equal to 2000. This will be M into 80. That would be 0.025 grams. So that means if you can convert 25 grams of water into 25 grams of ice, you will get the 2000 calories of heat required. Therefore, finally, you have 175 grams of water at 0 degrees and 25 grams of water has become ice, and the final composition is 0 degree. Remember, the temperature will not change until all the ice will melt. Are you clear how we did this? Now, I'll tell you something. Listen, when you do this process, when you take this material, and when you assume a common state, right? There are only three possibilities you can get. Either you will get heat is equal to zero, means what? Your assumption is right. The quantities were exactly sufficient to get 0 degrees ice. If you got a negative heat, means what? It is freezing back to water. If you got positive heat, then what you do? You're boiling the water to higher temperature. These are the three possibilities you can get. But just have a look at this. I'll ask you one more like this. Is the question clear? Everyone understood the process? So same thing. Can you do the B part, but this time this is 100 degrees. I just changed this numbers is 70, 100. Can you do this? 100 grams of ice at minus 20 degrees and 100 grams of water at 100 degrees are combined. Find the final temperature and the mixture composition of mixture. Same question. I just changed the numbers. Twenty grams of steam at 100 degrees is mixed with 80 grams of ice at minus 20 degrees. Find the final temperature and the composition. There, let's get B and C part. So in all these questions, this is one way to approach. Assume a common state and from there you start. Everyone should try. Get them. B and C, I'll give you 2 minutes each. Really, calorimetry, they can't ask you really anything more. So in this, there are three important things. The first important one is these questions. The rod height is increasing, center of mass, springs. This is one important model. Second important model is the graph. And the third important model is this thing, mixing of different substances. Right, Samyak, that looks right. Get this, everyone. B part, 100 grams of ice at minus 20 and 100 grams of water at 100. If you mix them, find the final temperature and the composition. Right, Shriyant. Right, Rudransh. Okay, let's see the second part. Same story, huh? I'll just duplicate it. I just have to change few numbers. So this is A. So this is B part. So what will change here? This is 100 degrees. This will be 100. This will be 10,000. So this will be 10,000. This will be plus 1,000. So look at the question. Huh? You are changing the question only. I have 200 grams of water at 0 degrees and someone gave 1,000 calories. So what do you think will happen? The water will boil, temperature will rise, right? Since it is positive, temperature will rise. We can say Q is equal to ms delta T. How much heat you have? 1,000 calories. What is the mass? Remember, 200 grams of water. S is 1 and delta T. Therefore, T is 5 degrees. And everything is water. There is no ice left. Is that easy? Making sense? So that is the thing. If you got negative number, you have to freeze the water to ice. So use Q is equal to M into L. If you have positive thing, then you have to raise the temperature of the water. Use ms delta T. Can you do the third part? 20 grams of steam and 100 grams, no, 20 grams of steam at 100 degree and 80 grams of ice at minus 20. Let's get this. Right, Samyak? Nee, Shreyansh. How to do this thing? Again, same story. You'll always start with a common state. What was the common state? 20 grams of steam, 100 degrees, 80 grams of ice at minus 20 degrees. So I'll assume a common state. Again, I'll take 0 degree water. Why? Nothing. Just you can choose anything you want. I'm just choosing 0 degree water. So for this guy to become into this, first you have to become water. You have to become 100 degree water. Then you'll become 0 degree water. This will become 0 degree ice. Then you'll become 0 degree water. So there are two phase changes on both the sides. So here we Q is equal to M into LV. This is 20 into 540. That's 10,800. Q is equal to ms delta T. I hope you guys are clear when to use ms delta T and when to use M into L. You can clearly see this is water, this is water. So temperature is changing. This is steam, this is water. There is a phase change. This is 20, 1 and 100. This is 2000. So for the ice here, Q is equal to ms delta T. 80 specific heat of ice is half, and this is 20. So this is 800 calories. 6,400 calories. Perfect. 80 plus 20, 100 grams. So we have 100 grams of water at 0 degrees. And the total heat that I have, when you have converted the steam into water, it released 10,800. Then again it released 2,000. Remember, all this thing is the heat released, the red one. And this thing is 800 absorbed and minus 6,400 absorbed. How much is this? 7,200, 5,200, 5,600 calories plus. So your question has simply become like this. I have 100 grams of water at 0 degrees and someone has given 5,600 calories of heat. The Q is equal to ms delta T. 5,600 is equal to 100 into 1 into delta T. 56 degrees. Everything is water. Is the process clear, everyone? Understood how we are doing this? If you got positive, you start boiling the water to higher temperature, ms delta T. If you got negative, you start freezing the water to ice. You'll be always left out with only those two options. If you got 0, means your assumption was exactly right. Any doubt on this? Clear with this? So this is about mixing of different things, quite an important thing. There, that's a little about calorimetry. The next thing is your KTG. We'll just finish off a little intro. Kinetic theory of gases, KTG. So we are going to primarily play with your ideal gas equation here. And remember, this is the basis for the next chapter, thermodynamics. So we'll not get into all this derivation and stuff. PV is equal to nRT. There, you already know this equation from chemistry. What is the each term? P is the pressure of the gas. V is the volume in which the molecules can freely move. It's not the volume of the container. If you guys remember the real gas ka equation, you get P into A into N square by B square into you get V minus NB. याद है ऐसा कुछ आएगा? That B is the volume of the molecules. Molecules can freely move. But in an ideal gas, we assume the molecule ka volume is negligible. So technically, it should be volume of the container minus the volume of the molecules. That is your V actually. So in ideal gases, we take volume of the molecules is negligible. Therefore, we can write V is the volume of the container. Yeah, but theoretically understand what it means. It's not volume of the container, actually. So in a real gas, it is V minus NB. That is the number of moles. R is your gas constant. Be careful, you don't use that 0.0 thing in chemistry thing. That is in atmosphere, liter and everything. We use 8.3 joule per mole Kelvin. This is the SI unit ka thing. In some books, it will be written 25 by 3. It's the same thing. T is the temperature in Kelvin. Clear with this? Then we have three processes. Primarily, we have more adiabatic and all that we'll see in the next chapter. So in the PV is equal to nRT. If you take isobaric process, so what is isobaric process? P is constant. So if P is constant, we get a V is equal to nR by P into T. That means in a VT graph, the slope is nR by P. So in a volume temperature graph, P1 and P2, an isobaric process will be a line passing through the origin. Which pressure is bigger, P1 or P2? you can clearly see slope is proportional to 1 by P. So more pressure, lesser the slope. P2 is greater than P1. Isochoric process, V is equal to constant. Here the equation will be P is equal to NR by V into T. That means in a PT graph, if someone draws a pressure and temperature graph, the isochoric process will be a line passing through the origin. Again, V2 is greater than V1. In an isothermal process, Boyle's law basically, your temperature is constant. So here the graphs will not be straight lines, these are actually rectangular hyperbolas. These are called isotherms. So higher the temperature, the farther you are from the origin. So isotherms away from origin have more temperature. There, so this is some basic idea about these three processes. We have something called adiabatic process, then we also have polytropic process and free expansion. We are going to see that in the next chapter, but in this chapter, we primarily deal with these three also. And I'm sure you must have done this in chemistry, right? This much you have an idea there. Okay, with that, we'll have a further day. Next week, when we catch up, we will continue from here. So remember, we have finished thermal expansion and we finished calorimetry. Two small ones, you can start working on that. I'll send you a sheet also on them. So the next thing we will do KTG. It's pretty good. It will not be exactly like your chemistry. We also have a lot of mechanics-based questions in this. So that is one. Okay, I'll see you guys again on Tuesday. We'll continue from here. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you guys again on Tuesday, same time. So yeah.